Beneath the Pacific Ocean, two colossal pieces of Earth's crust are locked in a slow-motion collision that has carved the deepest wound on our planet's surface. For millions of years, forces beyond human comprehension have been sculpting the Mariana Trench through a geological process so violent and relentless that it makes our most powerful earthquakes seem like gentle tremors. This isn't just a story about a deep hole in the ocean floor. It's the tale of our planet's most dramatic geological battleground. Most people think of Earth's surface as stable and permanent. The reality is that our planet's crust is in constant motion, shifting and grinding in a slow-motion dance that has been reshaping continents and ocean basins for billions of years. The Mariana Trench represents the most extreme result of these forces, where the very mechanisms that built our world are still actively carving its deepest scar. What makes this geological story truly extraordinary is that we can witness these planet-shaping forces in action. Unlike ancient mountain ranges or fossilized evidence of past geological events, the Mariana Trench is actively forming right now, driven by the same tectonic processes that will continue transforming Earth long after human civilization has vanished. Before we explore these incredible geological forces, drop a comment below telling me where you're watching from and how the weather is treating you today. It's fascinating to think that the solid ground beneath your feet is actually riding on massive crustal plates that are constantly moving, just like the ones creating the Mariana Trench. The story we're uncovering today reveals how our planet's internal heat and pressure create forces powerful enough to bend, break, and reshape the very foundations of continents and ocean floors. Understanding the Mariana Trench means understanding the geological heartbeat of Earth itself. The trench exists because of a fundamental geological process called subduction, where two massive pieces of Earth's crust meet and one is forced to slide beneath the other. The Pacific Plate, one of the largest crustal sections on our planet, is colliding with the smaller but more buoyant Philippine Sea Plate along what geologists call the Mariana Subduction Zone. This collision isn't a sudden crash, but rather an inexorable grinding process that occurs over millions of years. The Pacific Plate, composed of dense oceanic crust, is being forced downward beneath the lighter Philippine Sea Plate at a rate of approximately 2 to 3 inches per year, roughly the same speed at which human fingernails grow. While this movement seems incredibly slow by human standards, it represents enormous geological forces. The descending Pacific Plate carries with it layers of sediment, seawater, and even microscopic marine organisms that get dragged deep into Earth's interior. As this material descends, it encounters increasing heat and pressure that fundamentally alter its chemical and physical properties. The subduction process creates a deep oceanic trench where the descending plate bends downward into Earth's mantle. The Mariana Trench stretches approximately 1,580 miles in length and reaches maximum depths of over 36,000 feet below sea level, deeper than Mount Everest is tall. The geological violence of this process is difficult to comprehend. As the Pacific Plate flexes and bends during its descent, it creates fractures and fault systems that trigger frequent earthquakes. These seismic events occur not just at the surface but throughout the descending plate as it adjusts to the enormous stresses of subduction. The heat generated by this friction and the pressure from overlying rock layers cause profound changes in the descending crustal material. Minerals that were stable at the surface begin to break down and reform into different crystal structures better suited to high-pressure environments. What aspect of these geological forces fascinates you most? What topic in Earth's internal processes baffles you the most? Share your thoughts in the comments below and I'll research it for a future episode. As the Pacific Plate descends deeper into the mantle, some of its material melts due to the increasing temperature and pressure. This newly formed magma is less dense than the surrounding solid rock, causing it to rise toward the surface. When this magma reaches the seafloor, it creates underwater volcanic activity that forms new crustal material. The Mariana Islands themselves were created by this volcanic process. As magma from the subducted Pacific Plate rises through the overlying Philippine Sea Plate, it creates a chain of underwater volcanoes that eventually grew tall enough to emerge above sea level as islands. This volcanic island arc runs parallel to the trench itself, marking the location where subducted material returns to the surface as new igneous rock. The entire system represents a massive recycling operation where old oceanic crust is consumed at the trench while new crust is created through volcanic activity. The chemical composition of magmas produced by subduction differs significantly from those created at mid-ocean ridges or hotspot volcanoes. Subduction zone magmas contain higher concentrations of water and volatile compounds that were carried down with the descending oceanic plate. These chemical differences create more explosive volcanic eruptions and generate different types of igneous rocks. Hydrothermal vents along the trench slopes represent another fascinating aspect of the geological process. As seawater penetrates into fractured crustal rocks near the subduction zone, it becomes heated by contact with hot magma chambers deep below the seafloor. This superheated water dissolves minerals from the surrounding rock, creating chemical-rich solutions that eventually return to the seafloor through hydrothermal vents. These vents discharge water at temperatures exceeding 400 degrees Celsius, hot enough to melt lead, yet the extreme pressure prevents this water from boiling. The mineral-rich fluids from hydrothermal vents create unique chemical environments that can support specialized ecosystems based on chemosynthesis rather than photosynthesis. These geological processes literally create new habitats for life forms that exist nowhere else on Earth. The vent systems also deposit valuable minerals on the seafloor, including sulfides of copper, zinc, and other metals. These deposits represent concentrations of rare elements that are economically significant and scientifically important for understanding how deposits form. Like what you're learning about Earth's geological processes? Hit that subscribe button and turn on notifications. Your support helps ancient underwater mysteries continue exploring these incredible planetary forces. Each subscription means the world to me as we uncover the secrets of our planet's most dynamic environments. The age of the oceanic crust being subducted at the Mariana Trench provides insights into the long-term geological history of the Pacific Ocean. Much of the Pacific Plate consists of crust that formed at mid-ocean ridges over 100 million years ago, making it some of the oldest oceanic crust on Earth. This ancient seafloor carries a geological record of past oceanic conditions, including variations in sea level, climate, and marine biological productivity. As this material is subducted, it carries this historical information deep into Earth's interior, where some of it may be preserved for millions of years. Sediment cores collected from the trench provide detailed records of past geological events, including major volcanic eruptions, climate changes, and impact events. These geological archives help scientists understand how Earth systems have changed over geological timescales. The structural geology of the trench itself reveals the incredible forces involved in the subduction process. The trench walls show evidence of massive underwater landslides triggered by earthquakes, creating a constantly changing underwater topography. Seismic studies of the subduction zone reveal the three-dimensional structure of the descending Pacific Plate as it bends and breaks during its journey into the mantle. These studies show that the plate remains coherent for hundreds of miles as it descends, creating a cold, rigid slab surrounded by hotter, more plastic mantle material. The interaction between the cold descending slab and the surrounding hot mantle creates complex patterns of heat flow and chemical mixing. Some regions of the descending plate may remain solid and relatively unchanged for millions of years, while others are completely assimilated into the mantle. The geological processes operating at the Mariana Trench have global implications for understanding plate tectonics and crustal recycling. The subduction occurring here is part of a worldwide system that maintains the chemical balance of Earth's crust and atmosphere over geological timescales. Elements that are removed from the ocean through subduction are eventually returned through volcanic activity, maintaining long-term equilibrium in ocean chemistry. This geological recycling system has operated for billions of years and is essential for maintaining conditions that allow complex life to exist on Earth. The Mariana subduction zone also influences regional patterns of earthquake activity and tsunami generation. The geological stresses created by subduction can trigger major seismic events that affect populations throughout the Pacific region. Understanding the timing and magnitude of these geological processes is crucial for assessing seismic hazards and developing early warning systems for communities at risk from earthquakes and tsunamis generated by subduction zone activity. The mineral deposits created by hydrothermal activity at the Mariana Trench represent potential resources for future deep-sea mining operations. However, extracting these materials would require technology capable of operating in the extreme conditions of the deep ocean environment. The geological forces that created the trench continue to operate today, constantly reshaping the seafloor through ongoing subduction, volcanic activity, and seismic events. This dynamic environment ensures that the trench will continue evolving for millions of years into the future. Recent geological surveys have revealed previously unknown features of the trench structure, including deep basins isolated from the main trench axis and complex fault systems that control the flow of sediments and fluids through the subduction zone. These discoveries demonstrate that our understanding of subduction zone geology continues to evolve as new exploration technologies allow scientists to map and study these extreme environments in unprecedented detail. What part of this geological story intrigues you most? The massive plate collisions, the volcanic island formation, or perhaps the mineral-rich hydrothermal vents? Comment below and share which aspect of Earth's internal processes you find most fascinating. The study of Mariana Trench geology provides insights into similar processes occurring on other planets and helps us understand the fundamental mechanisms that shape planetary surfaces throughout the universe.